if you ask me to, but.
Okay, so I just want to double check the volume level right now before I get to start off too far. Is this good?
Yes, very good.
Okay, so first of all, I'm going to be going over several of the components that are in this the Worldwide Telescope ecosystem, and then drill in more on some specific portions of these. So we're going to be talking about the clients, and these are the Worldwide Telescope consumers of data that basically take the data in the Worldwide Telescope ecosystem and present it in an interactive way with a customer. We have APIs, which are our developers' ways of driving the ecosystem from code that they produce. We have data formats, and these are getting your data into a format that can be consumed by one of the Worldwide Telescope clients. We have tools that allow you to process data and turn them into the data formats that are friendly to the Worldwide Telescope ecosystem. We have some software development kits that are a collection of tools, code, examples, etc., that basically allow you to access the APIs and the data formats and make use of the clients. And we have extensibility mechanisms which are built into Worldwide Telescope that allow you to take Worldwide Telescope and, without necessarily developing anything, be able to make use of additional components and functionality. So the clients that we have are primarily three different types of clients. We have the Windows application client, which is a desktop and based application that runs in a variety of different ways. It can run in a kiosk mode. It can run interactively as a desktop application. It can be run in a cluster as part of a planetarium rendering. And essentially, this is the most powerful and most flexible of the Worldwide Telescope clients. It's the one that has the richest feature set in terms of interactivity and in terms of graphics processing. Then we have the HTML5 web client. This is a client that's designed to have the look and feel and visual identity of the Worldwide Telescope desktop client, but be able to deliver across to any platform and run on tablets, on phones, on desktop browsers, on different operating systems. This is under the most amount of development. It does not yet have near feature parity with the Windows application client, but because of the technology that's been evolving in the web, we feel that there's a lot of room for growth here in the open source community, and both the developers that have been part of the project, Ron and myself, and others, and also we feel that the open source community, this is an opportunity. There's already a lot of plumbing in there for WebGL. Once we turn WebGL on, we'll be at a lot of solar system functionality. For instance, in the solar system mode, we'll be able to use things like shaders and large catalogs and things like that. And so it's got a lot of room for growth. We also have an embeddable control, which is a minimized version of Worldwide Telescope that's designed for more specific feature sets. I'll drill into more details on each of these clients. Again, the Windows client, it's the richest feature set. It runs as a native application either through Windows directly by having a native Windows installation, but also it runs very well in virtualized environments such as VMware Fusion or Parallels on the Mac. It also runs really well in a cloud environment where you have reasonably decent graphics processing. And for instance, we had a workshop in Chicago a few months ago, and we actually fired up some Azure virtual machines, and we had people connect up to those machines from their Mac desktop client. So for instance, if you want to sign up right now for an Azure trial account, create yourself a VM, and then if you have a Mac, right, install Remote Desktop for Mac, install the VM. You can install the Worldwide set up a Windows server with a reasonable number of cores. The lowest end system performs poorly, but the higher end systems actually perform really decently and are a really good development environment if you don't have a PC and you're just running from a Mac and you want to run the full Windows client of Worldwide Telescope to author tours or to do development, to run Visual Studio and other things like that that are required for the Windows 3D. So that's another great environment. We use DirectX 11 extensively in the Windows client to offload all of the rendering workload and some of the computational workload. For instance, we have things like computation of the minor planets, and there's about 600 and something thousand minor planets that are all computed positionally in real time, and that would be impossible without offloading all of that to the GPU. We have flexible display modes in the Windows client that allow it to be used in power walls, 3D stereo, things like Oculus headsets, as well as full dome environments. The clustering allows you to have several different Worldwide Telescope machines that all run in parallel with each other, all controlled by a master. And this can be used for full dome environments, for running master-slave situations in kiosks, for being able to have interactive distance communication. For instance, there's a researcher in Germany who has a colleague in, I'm not sure where else in Europe, but somewhere else in Europe, and they have a couple of upside-down domes that they do oceanography with each other and interact and share data and share visualizations connecting up over the network like that. You also have the ability to lock down into a kiosk mode for dedicated interactive exhibits. That's a pretty powerful idea that you can actually build a tour that has very custom graphics and has buttons that click and have actions on them. They can go from slide to slide. They can answer questions. They can have an interactive narrative that allows you to have fork and move from different storylines or have menus, return back, etc. And this can all be programmed without having to actually be a software developer. You can just use the tools that are built in. Also, we have the LC API, which we're going to be drilling into later on in the session, that allows local and remote applications to send data and control messages so that you can integrate with your own software to be able to run the Windows client and be able to pump data to it from databases, from simulations, from any other sort of environment that you have that Worldwide Telescope may not natively understand. It allows you to be able to control and automate it. It also integrates with custom controllers so that you can do physical controllers. And right now we're supporting things like MIDI, Xbox controller, Kinect, and then the LC API. Again, we'll drill into this in greater detail. Allows any one of these controls to be mapped so that you can actually send HTTP web requests in detail. So the Windows client, in this environment that we build for Worldwide Telescope, we have this concept of that data is at different reference frames. So we have these nested reference frames. And at the reference frames, you can have we have intrinsic layers that are basically sort of shipped with Worldwide Telescope or as part of the Worldwide Telescope metadata. So for instance, in our solar system, we have the sun and a texture on the sun, and we have the orbits of the planets, and at the orbits of the planets, we have multi-resolution textures that you can zoom in on. You can flip these data sets to be able to layer additional data sets over them. Some of them, like we have latitude and longitude grids that can be turned on or off. You can create nested reference frames where, for instance, you can have an orbiting reference frame like the International Space Station, and then at that orbit you can place a 3D model. You could put a moon around a planet and then have a satellite around that moon and then plot data from the satellite's location. And so the reference frames are all controlled through something called the Layer Manager. And the LC API allows you to plug into that. And again, we'll get into more detail on that in the LC API. We also have a very rich built-in tour authoring and playback system that you can start out with simple slide-based shows and then move on to complex keyframed animation where you can actually set keyframes over time for any object that you have or any setting that you have in a worldwide telescope and do a very tight control over things. We have support for user-integrated data like 3D modelers, tabular data, orbital data, imagery, and catalogs, as well as a VO client that allows you to explore and search on virtual observatory data sets and load things like FITS images and VO tables and visualize them. We have a WMS client that allows you to get WMS client. Now, WMS, as was asked later, to explain some of these TLAs, three-letter acronyms. I guess this could also be two-letter acronyms, but in this case, WMS is the web mapping service, and it allows you to bring in data from the internet that is in this specification that's an OpenGIS standard. And we support both tiled WMS as well as WMS time series. We have an OData client, and OData is an open data standard for being able to query against data over the internet. And so you can actually create a tour that's visualizing data. Every time you load the tour, you actually fetch the data from that OData service. We have a deep integration with Microsoft Excel through the Excel add-in, and that Excel add-in, as powerful it is, uses nothing more than the features that are available to everybody through the LC API. So essentially anything that the Excel add-in can do, the LC API can do, and more. So that means that all that power is also available to anybody who wants to code against it. Moving on to the HTML web client. It's a hosted subset of the Worldwide Telescope features that's delivered in a cross-platform, plug-in-free, browser-based system. We're leveraging the Worldwide Telescope web control, which is a component which is available separately as part of the SDK that essentially the web client is a user interface layer that drives that web control. So the web control provides the functionality of visualizing things. The web client provides a user interface and all the infrastructure to actually use that embedded into a browser. We have to use the same WTML images and catalog sources that the desktop version uses. We can display the same sort of tiled images, tours, audio, and a significant number of the intrinsic WWT sets, like certain sort of constellation names and grids and other things like that that are part of Worldwide Telescope. Recently, we've added a basic solar system mode to that, so that the web client now has the ability and web control have the ability to actually have the solar system, including the actual keeping up with the orbits of the given planets and positions, etc. Some very basic lighting support. We have tour playback, but no authoring. The tours are also limited to sort of the traditional first and second generation Worldwide Telescope tours that don't have the keyframe timelines yet. Now, in the future, we're hoping that we'll be able to have playback of keyframing and things like that. But that's, again, part that we're hoping to work with developers in the open source environment to be able to, bring it up to feature parity.
Hey, Jonathan, just for a second, Carl has a question he wanted to ask you at this slide.
Okay.
Yeah, thanks. This is really informative. Thank you, Jonathan. On that previous slide, I'm just curious, in the basic solar system mode, at the end it said, but does not support travel beyond the solar system, but you didn't talk about that part. I assume that's referring to the solar system mode, but not to the web client as a whole, right?
Right. So the web client as a whole, so in the solar system mode, if you try to, there is no data outside the solar system. In Worldwide Telescope's Windows client, when you back out of the solar system, you see the Hipparcos catalog, and then the Milky Way, and then the Sloan Digital Sky Survey, and then you back up all the way to the cosmic background. We don't have all of those additional layers in the web client at this point in time. So it does allow you to do things like do the positions of Jupiter's moons, or find out where Mars is and the moon and such. But it is currently a limitation of the browser, so it doesn't have full one-to-one feature fidelity with the Windows client. So right now there is an HTML5 renderer that's what's turned on. So essentially we've built a 3D engine inside the web client and the web control that gives you the illusion that you're running a 3D system, and so it's using HTML5 canvas to draw everything. It's not using the GPU directly. Some of the browsers actually accelerate the canvas drawing with some GPU support, but it's a fairly basic vanilla. And shockingly, I was shocked that it actually worked to begin with. I think when we first presented it in Urbana at the IVOA, there were actually some other parties who came up and had researched it and said, well, maybe someday, but we can't do it quite yet. So I was when it actually ran on IE and Chrome at something like 180 frames a second in the Sky mode. I just couldn't believe that we could actually, push the bits out. Now the challenge is when there's lots and lots of data, JavaScript rendering falls over really quickly, and so we have a full WebGL pipeline that's actually built into the web control and thus the HTML5 web client, but it's not yet turned on. We were waiting to turn it on for the iOS release that was going to support WebGL inherently within iPads and things like that, which should improve the performance significantly. Unfortunately, that's when we had the reorganization, and the priority became rolling it out to open source and not finishing new features. Now that the open source rollout is complete, we're hoping to be able to come in and actually activate the WebGL, and when that happens, we actually may be able to get closer to feature parity, meaning we're going to have much better rendering of the planets, including altitude data, shading, lighting, etc. And you'll also be able to fly out of the solar system, have a Milky Way, and also have like the Sloan galaxies and things like that. Oh, one of the things I realized is Miguel's not here. And I wonder if I don't know if he's speaking of galaxies, right? Miguel should be here today, and we had dinner with him last night, and hopefully we can.
I'll shoot you an email, Jonathan, just to see if he.
Sorry, I just realized. I hope he's not like hanging out outside his security or something, or in the wrong. Okay. The feature parity. When we talk about feature parity, we're talking about sensible end user features. So there are things like MIDI controllers, cluster rendering, full dome that won't necessarily make sense because you are not going to want to run a planetarium, in a multi-projector environment by starting up 5 different browsers and having a WWT web client. I don't imagine anyone's ever going to want to do that. It actually might be, though, that we might have a simple, a mirror dome type planetarium support in a browser, so that someone with a Mac could actually run a mirror dome single channel worldwide telescope in the future. That might actually be possible using WebGL. So embeddable controls. This sort of crosses a line between a programmability and a control, because they do require that you embed it into a page somewhere. But I think it's actually possible to, just cut and paste the code for this little snippet into like a WordPress site or some sort of thing that just, a blog post and other things like that. So I don't know if you want to call it a software development kit if you can cut and paste it. So it kind of blurs the line, because it does give you the capability of configuring it configuring a worldwide telescope viewer to be able to play tours, be able to visualize a certain data set, but have a very low barrier of entry in order to code do it. It also only implements a subset of the user interface, but does have a button so that you can click to the full version of Worldwide Telescope. Now we get on to application programming interfaces, and these are some of the things that hopefully we can get you guys started on for integrating into your code. First of which is in the Windows application, we have the Layer Control API. One of the aspects of the LC API, which is kind of cool, is that it's very language agnostic. It actually, even though it's a desktop application, it presents a web services interface so that essentially anything that can talk to an HTTP connection can control Worldwide Telescope. And so there's been a number of people who have written Python layers or other types of work on top of that that allows you to go ahead and communicate with the LC API. And again, we'll drill in later in that session. The web control, of which the web client is based on, but the web client is not the web control. The web control allows you to embed an Worldwide Telescope rendering engine into your website. This is not going to have a whole lot of UI support. You'll have some interactivity, but it's not going to have thumbnail browsers, selections, dialogues, or anything like that. It's stripped down to basically the rendering capability. And this allows you to put a Worldwide Telescope and deeply integrate it into your website. So if you want to create a custom data visualization, then you can do this. For instance, the LIGO Gravity Observatory has a website that you can go in and see all the LIGO events on the sky and browse around, and it connects up to the LIGO database and creates these error circles for where the sources have been detected and things like that, and allows you to interact with it. That basically it isn't a feature that would work inside the native web client, but as part of the web control and their coding, they can glue together our visualizations with their data. And so that's something that is a pretty powerful option for people wanting a web-based Worldwide Telescope visualization. We also have a set of web services APIs. These allow you to get things like, hey, tell me about all the catalogs that you have. Tell me about all the imagery, the studies, the image sets, and these services can return things like a WTML file that describes all of the surveys or studies available. Then you can say, okay, get me an icon for that. Get me a tile for that. Get me a whole set of tile pyramids. So you could actually build a completely different service that used your own code for the front end, but then just used our back-end services to be able to fetch data. So theoretically, you could plug in, a Google Map control, or Bing Map control, or your own custom rendering or your own custom services, and be able to get at that data. We also have a Windows Client Socket API for the Windows client that allows you to connect up from, right now we do this in the Connect application, so that when you move your hands and we detect that we want to zoom in or zoom out or do things around, we can very quickly and interactively access the Worldwide Telescope, so you can have very smooth interaction with it. And this is it's a private API, but it is available, and the Connect control source code basically shows you how to access it. It can also do some interesting things like put up different reticles that can be controlled individually, so that you can have calibration points. There's a University of Washington capstone class in their computer science department in which they used this interface in the Worldwide Telescope and had voice interfaces and pointing with Connect, so that you could actually point at a particular star and have a reticle that would follow your pointing. And they used it to be able to actually calibrate the eye finger line, so that you would look at your finger and it would figure out exactly what point that would intercept on the dome. So it's available, and it's interesting, and it's pretty high performance compared to doing the same sort of commands through the LC API, because it's constantly connected. And let's talk about some of the data formats. WTML is something you're going to hear a lot with Worldwide Telescope, and this is an XML extension that contains things like folders and images and places, and these are things so that when you want to have a catalog of images or a catalog of objects to go to, you can describe what you need to do to be able to browse these things in a WWT client. So when you have a set of thumbnails that you're browsing, and you click on the thumbnail, and when you click on the thumbnail, there's, say, a foreground and background image set that's available, or it's going to launch a tour. And so this is basically our way of just capturing the different types of data that Worldwide Telescope and providing the metadata necessary. When you give a WTML file to someone, it's just a matter of text and metadata. But what it does is it knows how to phone home for the actual source of the data. So when you add that to a tour, that metadata is in the tour, and the tour itself doesn't have any of the imagery. It doesn't have the data specifically, but it has the metadata about where to actually go and grab that data. Worldwide Telescope, our imagery is all delivered. One of the reasons it's fast and you can look at massive images very quickly is because we create tiled multi-resolution image sets. And what this is say you have a really big image from Hubble that's a mosaic that's, say, several gigapixels. That image may not even be loadable on a consumer-grade PC in memory, period. Right now, maybe the computers are catching up to maybe where it's actually possible to load it in memory, but the download time would be prohibitive, especially on a slower connection. And so the user would not see anything until every single bit of that image was downloaded. With Worldwide Telescope, we turn that image into a very small 256 by 256 image that's just a matter of a few kilobytes. So it can be loaded nearly instantly on the network. And then when you start zooming into that image, we divide it into 4 images that each take a quarter of that space and are 4 times the resolution. And so then there's 4 256, and so on and so on. And this is called an image pyramid. And these image pyramids are delivered by streaming the appropriate image that you need from the pyramid over these internet services. They're in what are called quad trees. So every single element can be broken into 4 individual elements, and you only ask for the elements that are visible on the screen at the screen's current resolution. So right now, if you can play a HD or 720p YouTube format, you can browse the universe in real time and be able to bring all the data in for as large an image as you ever want to look for, because you only need to essentially bring in a screen full of imagery at a time. In this, there are several different ways that you can project images that Worldwide Telescope understands how to display. The one that used to be unique to Worldwide Telescope, we created it for Worldwide Telescope, and now it's been adopted by a number of other groups, is something called TOAST, or Tessellated Octahedral Adaptive Subdivision Transform. That's a mouthful, so we just call it TOAST. It's a spherical projection without singularities that's delivered through a quad tree structure. That makes it kind of unique. There are other systems like HealPix and such, which start out with 12 pixels that then get subdivided or something like that. And they can't be represented by a quad tree. The representation of being able to start out with a single 256 by 256 image and zooming in on that, this delivers a very smooth thing, and there's no part of the Earth that's particularly better or worse at representation. With other projections like Mercator, you actually cut off the poles altogether. Equirectangular, you have a singularity at the poles, so that basically the 1 pixel at the equator takes the same amount of data download as 1 pixel high line all the way around the equator. So that means that as you zoom in, eventually you get to a near infinite amount of data required to zoom in any further, which is kind of a bad thing. Now, we do support these other formats, like Mercator and Equirectangular, for compatibility with other data sets. But TOAST is our preferred method because you can zoom in all the way on a pole and not have any artifacts, or any place else in the sky. And it's not a precisely equal area, but it's close enough that the error isn't really significant. Miguel actually made it here, so we're glad to see him. Okay, so the other types of things, when you have a small area of the sky, we should... Yes?
I'm just wondering if the Mercator projection works.
The question dropped out.
I was wondering if the Mercator projection works on the web client as well.
Yes, the Mercator, all the projections for the imagery work on all the clients. The thing is that some of the disadvantages of individual projections is that Mercator and Equirectangular, especially Mercator, were designed to be viewed as flat maps, and therefore some of the features that they have were designed because people were making flat maps and they wanted to minimize a certain type of distortion. So a Mercator map, as you go closer to the poles, everything gets bigger, and so that's why if you interview a senior in high school, they think that Greenland and Africa are roughly the same size, even though they're a more order of magnitude different in actual size. Mercator represents them as being similar. And so there are some really downsides to that. But with Worldwide Telescope, we're using these projections as a way of storing data as an intermediate product, and then we're actually drawing them in spherical space, where everything is actually how it should be instead of flattening it out. And so some of the properties of Mercator or Equirectangular that are okay for flat maps make them really a poor choice for an intermediate format. While TOAST looks like crap as a flat map, but as an intermediate format to deliver the data, because you're never actually going to look at the flat pixels. You're always going to project it back into a sphere. And as an intermediate projection, it's actually very good. Okay, then the other aspect is that we have the ability to load in an AVM tagged VAMP image and then directly view it. But remember, if you do that, you have to load the entire image into memory before you can view it. We have an optimization for the web client that if you load a VAMP image, it actually gets sent in the background to a service that chops it up into tiles and then delivers it through a tile interface. But it still has to do a server-to-server connection, download the entire image, and then chop it. The next time a person loads that same AVM image from the same URL, they'll already have a tiled version, so it will actually perform fairly well. So it is a reasonable alternative when you're using the web client for delivery to be able to have sort of a chopped on the fly, because it's only on the fly for the first person who uses it. Okay, some of the other things that we can deal with in Worldwide Telescope are 3D models. We can bring in a 3DS file and OBJ files. We actually use some extensions. Sure.
Jonathan, we have a question here. Just go ahead.
Yeah. So hopefully there's two quick questions. On the WTML file, the question is: are the tours, if you did create a tour, are the tours instructions contained within that? And then I'm also just in terms of the tiled images, those are all being hosted on a server somewhere, and is that, I mean, is that who owns sort of all those images and stuff?
Okay, so so the question was, what to the WTML file? Does the WTML file tour store in a WTML file? And then where are these images hosted? So the images are hosted all over the web on publicly available websites. The Worldwide Telescope project has a server that has a lot of popular data that we curated and processed that's stored up in an Azure servers. And right now there is a grant that Microsoft has made for the next few years for the payment of the costs associated with that storage. But there is only a small percentage of all the data that Worldwide Telescope uses is on those servers. Worldwide Telescope uses a lot of data that is hosted on websites all over the world, and WTML is the way to basically find it. Once someone publishes a WTML file, you don't have to think about where that data is coming from. The only reason it would matter is if someone pulled it offline and then you couldn't get to it. And the reason we have most of the curated data on our servers is that we can ensure that that data at least will stay online. The other question was the tour files, and the tour files are not stored in WTML. They are stored in a proprietary format that, of course, it's open source, but we would rather people use the clients to access the tours rather than trying to manipulate them by modifying the bits to them. So we don't recommend modifying the tours directly because they're a binary file with multiple data streams and such, and the Worldwide Telescope code does have code to access that, and people should take that code and move it into another client if they want to read tours and write tours. They should borrow that code from the WWT clients rather than try to roll it themselves against a data format. Was there did I answer all of the components of that question?
Yeah. Would the API know if the data existed if you went out to request something that had been pulled offline?
You would get a 404 and so the data would not, and most of the clients won't give you an error so much as you won't see anything.
Okay.
So there is sort of a silent failure mode in that you just don't see anything when it comes in. There are some debugging tools you can use to see why something failed by getting the URL or looking at the WTML file and constructing the URL for a root tile. And we'll go into a little bit more detail about how those are constructed. Okay.
Can I ask a question that I would pause?
Sure.
We might be getting to this later, so you can just punt if that's right. But when you were talking about the LC API, is there a way to get to the on GitHub to get to the code that's made, for example, like the SDSS survey, 3D Explorer, and look at that to use that as a template to build something similar, or is there a different way to interact that we should do?
Okay, so so for instance, visualizing the Cosmos or SDSS galaxy features.
Yeah, just
okay. So the LC API, isn't how that feature is implemented. But there are other you can use the LC API to push data into Worldwide Telescope for viewing. So, for instance, Andy Connolly at UW took some data from some simulations he was doing for LSST and pushed some of the pencil beam views of the galaxies from the simulation and put them into Worldwide Telescope to visualize in Worldwide Telescope, and then flew through them. And so it's possible to use LC API to do similar type of functionality to what we do with the galaxy. Miguel, this weekend, we're hoping to, as part of the workshop, import a new set of data that's got 5 times more galaxies or 10 times more galaxies than the current feature. So, but that will probably do by opening up the source code for the client. Okay, I'm going to get back to finishing up the slides. I think it's 8:30 when this expires, Doug, right?
We have a little bit of fudge room, about 15 minutes if we have to. So keep going. Don't rush.
So we support 3D models in 3ds and OBJ file format. 3ds is a binary format. OBJ is actually 2 different files that you would have, an object file, OBJ file, and a material file. And what's really cool about these is that the material file allows you to create textures and specify textures, specify lighting behavior and things like that. And the OBJ file, you specify the vertices and the faces that you're going to use for your model. But they're all text-based, so you can write these. So you have a simulation of, say, the galactic, or the cosmic structure or something, and you want to create surfaces for these. You could just output the vertices and the indices for the triangles and the textures that you want to display on this, and then just output them as text, and then use the LC API or just file open to be able to open up these files and view them in Worldwide Telescope. Random tabular data, you can just bring that in, and through cut and paste or the Excel plugin or through the LC API, you can bring in tabular data and then map the rows and columns of that table to visualizations in Worldwide Telescope. We've already talked about WMS a little bit. That's the web mapping services, and so you can bring in tiled and time series data for that. VO table, that's for the virtual observatory queries, and you can bring in VO tables, and they're another source of tables that you can then map different columns to. FITS files and the flexible image transfer. What's the S in FITS? Anyway, And that allows you to have a subset of FITS files that are TAN projected that you can load in. We don't support FITS tables yet, and that's something someone could add with open source. And I don't think we support galactic coordinates FITS right now, but we support the WCS and TAN projection, which is the most common variation of it. We also support shape files, the OGC format, and well-known text. And this allows you to have things like contours, borders, and this is important for people in GIS thing for Earth science visualization. So Ryan's folks probably can make use of this. One of my colleagues, Rob Fotland, took like shape files that were showing the sea ice extents over the years, and we created a time series layer set in Worldwide Telescope, and then when you played through time, you could actually see the ice, where the ice for sea ice on the North Pole was moving up and down over time, and watching how less and less of the poles were covered with ice over time. OData, we've mentioned already, and then two-line element. So if you have orbital data, flexible image transport system, Jessica is pinging me. So that's the FITS file format. All I know is that it gives me FITS. But two-line element orbital data, you can actually bring in bulk data into Worldwide Telescope and view a bunch of orbits around a planet, or using TLEs, and that can be done for bulk, or you can actually create an orbital reference frame that then you can plot data on that. Let's see where. Okay, so moving on to some tools on there, and again, I appreciate that. Trying to, this is a lot of stuff that we're packing in here, and you probably won't be able to retain all of this, but I'm hoping that at least, getting an overview of this will let you know where you can look for some of these tools, and sort of understand that there's a lot of these tools that are available, that if you have a problem, that there's already some solutions that you can look for, and where to start to drill into it.
This is Doug. Quick, Mark just made a point that. Do you want to just give a quick thing about what KML support we have in Worldwide Telescope?
Oh, yeah. Well, that's supposed to be secret. No one is supposed to ever know about that.
Okay. We'll take that off YouTube. Don't worry.
Okay. So, well, KML is. KML is there is two different versions of KML. KML is the keyhole markup language, and it was Google bought a company called Keyhole with a product called Keyhole that then renamed it Google Earth, and so the KML file still has the legacy of the Keyhole name in it. So it was KML. And what it was is a descriptive language for drawing things on the surface of the Earth. KML was proposed as a standard for the OGC, or Open Geospatial Consortium, and it was approved. But the version of KML that's approved by OGC is different than what Google Earth and the old Google Earth standards were. And so what ended up happening is that most of the KML in the wild is not OGC compliant KML. It's a mismatch of various versions of KML, and Google made this decision that the Google Earth client would read very loosely. So in other words, if you have errors or mismatches in versions or complete junk in your file, Google Earth will still read it and display something. And so people have often built a lot of KML that isn't compliant with the standard, and since Google Earth loads it, they think it's okay. And so this became a problem. We implemented an OGC compatible client in Worldwide Telescope, but we never officially turned it on because most of the KML in the wild was not legal, but Google read it, and because the OGC can't read it, it created this situation where people said it must be valid because Google Earth reads it, and we say it's not valid, so you've got a bug in your code. But unfortunately, Google does not describe how to read things as loosely as they do, right? And so this is a problem in standards where if you really want a standard to be interoperable, you need to make your product tightly compliant with that standard, because there's only one way to be tightly compliant, but there's many, many, many different ways to be loosely compliant. And so interoperability requires you to have tight adherence to the standards so that you know what works and what doesn't work. So if you want to mess with KML, you can open a KML file in the Worldwide Telescope. If it's tight OGC compliance, you should be able to use most of that functionality in Worldwide Telescope. If it's really loose, it may not work at all. So your mileage may vary. You may party on it, and if someone wanted to volunteer to figure out how to make our KML viewer, you know, as loose as Google's is somehow, I wouldn't mind doing that at all. Anyway, any other questions of KML? I probably spent too much time on it already.
No, that's it. Just Mark just wanted to make sure people understood the situation, so that's good. Thanks.
Okay, yeah. So some of the tools that are available right now are, we have something called a sphere toaster, which if you take something that's already a panorama, a all-sky image that's in equirectangular format, it will turn it into a toast tile pyramid, either in galactic or celestial coordinates, and create the pyramid and WTML file. We have Study Chopper, which allows you to take a small to medium size image study and turns that into a tan projected tile pyramid with WTML. We have our AVM import tool, and let me go ahead and actually do a quick demonstration of that here. I'm going to go ahead and bring up a web browser, and you go into Worldwide Telescope and you go to the Import Image in the Developer tab. This tool will let you take virtually any image that's on the web. I'm going to search for something, let's see, M51 here. Oh. Okay, so let's take this image here, and what I'll do here is copy this image. So we're copying the URL address, we paste it into the importer, and then we go ahead and load it. Now, in all likelihood, this is not AVM tagged, and so it's probably going to complain that there isn't AVM tagging on this. So it's complained that there's not AVM tagging on this. Now what we can actually do is put in some image credits and things like that, but and we could enter the right ascension, declination, and scale and rotation ourselves, but that would be a pain in the butt to get. We can click Solve with astrometry.net, and what this is going to do is it's sending that image up to astrometry.net. It's going to plate solve that image and return us the celestial coordinates and the scale and rotation and everything like that from the image by doing a plate solve on it, and then that will come back to us and we will be able to zoom in on that image, assuming this works. So it may take a few minutes. Anyway, while that's working, I'll head back to the slides for a second.
Do you have a question about an acronym?
Yes, on AVM.
Oh, AVM.
Astronomy visualization metadata.
Thank you.
The writer of the standard just defined it, so there you go. Okay, so we also have tools in the SDK. The tile SDK allows us has a bunch of pre-built tools in there as well that allow you to do some of the work. So I'm wondering if astrometry.net is up and running right now because it seems to be taking its sweet time, but we'll check on that later. Okay, I better hurry it up a little bit here. LC API, we're going to be talking a whole hour on it. I won't get into a terrible amount of emphasis on that since we're going to break it out. Our tile SDK, this is an SDK that allows you to create an image pipeline that will process imagery, elevation data, bathymetry, catalog data, etc., that you have in some format and turn it into tiled multi-resolution versions of that data that are compatible and performant in Worldwide Telescope. If you have some very specialized needs to process data that's too big for the out-of-the-box tools, this is where you go. I've done stuff with Mars high-rise, DEM models. I've done, this bathymetry projects, all sorts of stuff. It's got all the tools you need to do just about anything with tiles. We also have the Terapixel project, which is how we created the DSS Terapixel all-sky imagery, and that's something that the entire project, including all the everything you need except the original DSS plates, is all available there, and it's all open source. It's not on our GitHub project, but it's available in a separate open source project. Other tools that you have, IPAC Montage now supports Worldwide Telescope compatible toast formats and tile pyramids. And so you can actually use Montage to process large data sets. And if you're familiar with Montage and have the environment for it, it's a great tool for building these sets. NASA Skyview also provides toast projected data. So if you put data into Skyview or have data in Skyview that you want to get out, you can get it out in toast projected tiles and create pyramids with that. We'll talk about this more later in the deep dive into the client. So I think I'm going to do the last slide here, which is just an overview of the Get repository. These are the homes of where Worldwide Telescope code is available for. And so GitHub is a source control, public source control for open source projects that allow you to share data. And so the way it happens is all of our projects and everything you need to build them that isn't publicly that isn't already publicly available is put onto the source control system in GitHub, and you can clone these repositories and then install the prerequisite tools like maybe Visual Studio in some case or a text editor or whatever. Get all the copy of the source code and allow you to build everything that's in Worldwide Telescope yourself on your machine, on your servers, on your laptop, and then you can edit the code, modify it, compile it, and if you have a new feature that you want to then give back to the community, you can submit it as a pull request, and then we'll integrate that back into our main branch of the source code, and then we can do builds of this that then are distributed to everybody. So this is how the whole point of why this workshop exists, is so that you guys can not only use this code, but anything you build and create, you can contribute either by contributing back to our open source project or creating your own GitHub with your projects that you share with other people so that they can make use of the work that you do. And I think that pretty much covers the ecosystem overview. Again, it was like drinking from the fire hose. I'm going back here, and astrometry.net resolved the image. Here is our right ascension, our declination, our scale, our rotation. And now we can save and import. And let's take a look at this. We are now zooming in on this image, which is now a tiled multi-resolution image. And as you can see now, we can zoom in and we can crossfade. And you can actually see there's the real image there. And that AVM file can then be shared with people.
So John, this is Doug. This has been great. One of the things I was kind of thinking as a hack, would it work to do a FITS importer that would create a service that could just do a FITS to to AVM tag JPEG and then image import from that, similar to going through astrometry.net as an intermediary before it gets to the image importer? Is that something that could reuse a bunch of code if we put in some different code to do the FITS to JPEG conversion?
Sure. If someone had some FITS to JPEG conversion, we could actually make the tile, add that to the tile converter, and stack the astrometry.net on. So we could stack on the AVM data. If there's WCS data already in the file, we could export it as AVM tags, and then the image would load it without having to solve it. But if there weren't adequate WCS in there, then we could use astrometry.net to solve it. The issues would be image stretch and things like that, colorizing the image, and some of those things are actually best done in FITS Liberator and Photoshop rather than as an automatic process.
Right.
But you could create an automatic process for that.
Okay, cool. Yes, thanks for the hack in the afternoon. So, thanks, Jonathan. Does anybody else around the table have any questions? I know most of you guys were on mute, but if you have a question, now's the time to pipe up. Okay.
How do I stop sharing this mess?
Oh. Infinity loop. Okay. Yeah, thanks, Jonathan. That was really great. I think that was a really good high-level view of kind of all the pieces of Worldwide Telescope.